Hey guys, so it's just this week's video of all the questions we ran through last week. So yeah, as always, if I've forgotten any, let me know, but we'll just jump straight in. Okay, so I think we started with a little bit of functions just to kind of get a refresher into our brain because we're going to deal with functions a little bit later in the video, but this time to do with logarithmic functions. So I just threw this question in just to kind of give us a refresher on what functions are, what they look like, the notation used. So yeah, let's jump in. So it says, our function x squared plus 5x plus p, where x is just a real number and p is between -3 and 8, and p is an integer, blah, 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 whatever. So it's telling us this is our function, and we want to find the value of p for which x plus 3 is a factor of f of x. Okay, well, there's lots of ways to do this, but first let's just draw out kind of what our function looks like. So it's going to be some kind of quadratic because we know it's an x squared. We don't know where it crosses the x-axis yet, but that's okay. So just to recap, so this here is going to be our x-axis, and this is going to be our output. So whatever we sub into the function, say we go across 3, and we go down till it hits, or up until it hits the line, the function, and then we go across to the output and see what output we have. So this output would be 3. If we went across 4, so this would be 4 here, and then we go up to hit the function, and then see what it gives us. This would be f of 4. We went out 5, and then we went up to hit the function. This would be f of 5. And these would all just be numbers, so this could be like -2 is equal to that, 5 is equal to 4, and 7 is equal to f of 5. So f of something, g of something, z of something, like the f is just purely a letter, like it can be any letter. So f of something is just going to be a number. It's going to be an output. And this here, so this is our output, and this is just our rule for when we sub in x. So we sub in x into the rule, and we get some kind of a number as the output. That's basically what I want you to take away from that. Okay, great. And another thing about functions is we know factors multiplied together are going to give us the rules for the function, so the function itself. So factors multiplied, so factors look like x plus 3 and x plus 2 or something. So these multiplied together are going to give us some kind of a function, and that's going to have an x squared and an ax and a px and all that kind of thing. Okay, so factors multiplied together give function, and roots subbed into functions give 0. So roots are solutions to the functions. So if we sub in 4, say here, or this would be like -4 because we're on the negative axis. So we go across -4, and we go up or down till we hit the function, but we find that we're already on the function. The function crosses the x-axis. So we don't actually have to move up or down anything. So here our output here is 0, because when we hit the function, we go back across to get our output, we're already there. So this here is 0. So our output of our function at roots is 0. Okay, great. And those two bits of information are going to help us solve this. So it says find the value of p for which x plus 3 is a factor of f of x. Okay, well, we know factors multiplied together give the equation. So let's write out our equation. So we want x squared plus 5x plus p. And we know factors multiplied out give the equation. Now we don't know what the other factor is, so let's just call it a. And let's see what we can do. So factors multiplied out, so let's multiply them out. So x squared plus 3x plus ax plus 3a. Okay, then there's a common factor here in the middle with the x. So x times 3 plus a plus 3a. Okay, and now we know that factors multiplied give the actual equation. So this is going to be equal to this. And now we can just kind of compare things. So we can see that the x is multiplied by 5 over here, and the x is multiplied by 3 plus a over here. And then we tack on a p at the end, and we tack on a 3a at the end. And this x squared at the front is just doesn't change. Okay, so we know that we have two equations now from this. We have 5 is equal to 3 plus a. So we have 5 here is equal to 3 plus a. And then we have p is equal to 3a. And so we have two equations, one on top of another, and that is simultaneous equations. Okay, great. So simultaneous equations, but we know that this is the second type of simultaneous equations because we have an addition up here and we have a multiplication down here. And so these are operations of different orders, so we can't kind of add them together and cancel any variables off because there's nothing to cancel off. We can't separate this a from that 3 and take it off that a. So what we're going to do is we're going to use the equation with the easier equation, find a variable on its own and sub it into the more difficult equation. So let's do that. So if we take this equation up here and we just bring this 3 to the other side, so we do 2 is equal to a, great, now we can just sub that straight in. So p is equal to 3 times 2, p is equal to 6. Okay, great, so we've done that. We find the value of p for which x plus 3 is a factor. And we know x plus 3 is a factor because it's multiplied by another factor to give us the equation. And that's how we use that bit of info. Okay, great. Another way we could have done this question is by utilizing roots. So we know x plus 3 is a factor, and roots and factors are closely related. So if we have x plus 3 and we let that equal to 0, that's going to turn it into a root. So then we're going to have x equals minus 3. And then we know that roots subbed into equations, so f of minus 3 is going to be minus 3 squared. So everywhere we see x, we're going to sub in minus 3. 5 times minus 3, and then p. Okay, great. So minus 3 squared is just 9. 5 times minus 3 is minus 15, and p is just p. And we know when we sub in a root, always equal to 0. Because when we cross the x-axis, we're going to cross it at the roots, and that's going to be equal to 0, because we don't have to go up or down to hit the function at any point. Okay, great. So this is 9 minus 15 is equal to p, and that's equal to 0. So now we just get p on its own. P is equal to 6. And that's the same answer that we got before. Great. One last way we could have done this is more factors. So if we know factors multiplied together, so x plus a is equal to x squared plus 5x plus p. So factors multiplied together give the equation, but that also means that factors divided into the equation give the other factor. So if I divide x squared plus 5x plus p times the factor that I know, I'm going to get x plus a up here, and I'm going to get a remainder of 0. So they should divide in evenly. Okay, great. And so we're going to divide in. We're going to be left with some kind of a remainder with p down here. And just spoiler alert, you're going to get p equal to 6, because we're going to end up with p down here because x doesn't multiply or divide into p evenly. So we're just going to take it down as a remainder, but we know our remainder has to be equal to 0. So we're going to end up with something up here. I think it's x plus 2. So it's divided in evenly. We've got two factors now, but our remainder should be equal to 0. And for it to be equal to 0, that means p has to be equal to 6. Because then if we sub in 6, then 6 minus 6 is 0. So in this case, p would equal to 6, which is what we'd expect. Okay, great. So those were kind of 3 different ways of answering part 1. And we'll move on to part 2. Okay, so part 2 says, find the value of p for which f of x has roots which differ by 3. Okay, well, if we draw out what that kind of means, that means if our equation looks like this, we're going to have 2 roots, and they're going to be 3 units apart. So we're going to have some kind of a root. We don't know what it is. It could be alpha, but we know that it's 3 units apart, so this one down here is going to be alpha minus 3. And so this is going to be x is equal to both of these, because we're going to go out alpha here, and our equation is going to cross the x-axis, and we're going to go down alpha minus 3 down here. Okay, great. So our roots here are alpha and alpha minus 3, and that kind of tracks because we know they're different by 3. Okay, so how are we going to find the value of p for which f of x has roots which differ by 3? One way to do that is we know that factors and roots are closely linked, and we know that factors multiplied together are going to give the actual equation for f, and then we can do the same thing we did before, where we can compare terms and just find out what p was straight away. So let's do this. Let's turn these into factors and then multiply them together and let them equal to our function. Okay, so how do we let them equal to factors? Well, what we're going to do is if we had something like this was a factor, what we do is we let it equal to 0 and we bring the 3 to the other side, so that would be minus 3. That's what we had in the last question. This time we have x equals minus 3, something like that, and we want to turn it into a factor, so we're going to bring this over here and just put brackets around it, and that's going to be 0. We can just drop that. This is our factor here, x plus 3 in brackets. So we're going to do the exact same, but now we just have alphas. So let's bring the alpha minus 3 over to this side. So that's be minus alpha plus 3. That's one factor, and then we're going to have x minus alpha is the other factor. Okay, great. So these two multiplied together are going to give our function x squared plus 5x plus p. So let's do that. Let's do x squared minus alpha x plus 3x minus alpha x plus alpha squared plus 3, or minus 3 alpha. So I've just multiplied all that out. Now we can do the same thing we did before, where we have like terms here. So we have a common denominator of x. So if we do plus x times minus alpha plus 3, and then we have a remainder of alpha squared minus 3 alpha. And that's going to be equal to x squared plus 5x plus p. Okay, so our x squareds are the same, that's fine. Our x's, so here we have 5, here we have minus alpha plus 3, and our remainders we have p, and we have alpha squared minus 3 alpha. Okay, great. So let's do the exact same thing we did before. We had 5 is equal to minus 2 alpha, so I'm just combining those two there, and then plus 3. And then we had alpha squared minus 3 alpha is equal to p. Okay, basically we want to find p, but we have the alpha stuck in the way. And so we need to find something for alpha so we can sub it in and find out what p is. So we only have alpha in this top equation here. So we can get alpha on its own and find out what it is. That's pretty straightforward. So bring this 3 to the side, so that's 2 is equal to minus 2 alpha. And so then divide by minus 2 on both sides, so minus 1 is equal to alpha. Okay, now if we sub that into here, we'll get minus 1 squared minus 3 times minus 1. And that's going to be equal to p. And so minus 1 squared is just 1. Minus 3 times 1 is plus 3. And so p is equal to 4. And so that is our value for p. So f of x had roots which differ by 3, so that meant it had these two factors. We multiplied them out and just compared terms and found out what p had to be. Okay, great. That was kind of similar to what we did in the above question, but there's another way we can do this. And that is kind of similar, but instead of turning them into roots, we're just going to keep them as x equals alpha is a root and x equals alpha minus 3 is a root. And there's a very special form of quadratic equation we can use that tells us something about the roots. And this is just a little trick that you might use to help speed up in exams. If you want to, that's great. If not, and the other way makes more sense to you, continue doing that way, just as long as everything makes sense to you. Okay, great. So the one thing about quadratic equations is that you can write any quadratic equation in this form: x squared minus x times a plus b plus a times b, where a and b are the roots. So a and b here are the roots, and any quadratic equation, any of them, can be written like this. And just don't forget about this minus here. So if we actually go ahead and write this equation like that, x squared, we want a minus x because we have the minus x here. And so how are we going to get the plus 5x when they're multiplied? Well, we're going to need a minus 5 in the brackets as well. So then minus 5 times minus x is going to be plus 5x. And then we're going to have the plus p at the end, and it's going to be ab. Okay, so our roots are alpha and alpha minus 3. And we know that when we have it in this form here, minus 5 over here is going to be 1 root plus the other. And this here is going to be 1 root times the other. So this is going to be, let's let this equal a. So a is alpha, and b is alpha minus 3. just to not confuse matters. So these are our two roots, alpha, a is alpha and b is alpha minus 3. So let's do a is alpha plus alpha minus 3, and that's going to be equal to minus 5. And then we can do alpha times alpha minus 3, and that's going to be equal to p. So same thing, we have two equations. So we have minus 5 is equal to alpha plus alpha minus 3, and we have p is equal to alpha times alpha minus 3. And so things should look kind of familiar, because if we rearrange these, you'll get 5 is equal to minus alpha plus 3, and p is equal to alpha squared minus 3 alpha. And so these were the two simultaneous equations that we had before. We just took a different route to get them. So if we combine these two alphas, that's minus 2 alpha plus 3, and then p was alpha squared plus 3 alpha. So then we would take this easier equation, find alpha. How are we going to do that? Well, bring the 3 to the other side, so that's 2 is equal to minus 2 alpha. Therefore, alpha is minus 1. Sub it in here. Minus 1 squared minus 3 times minus 1. P is going to be 4. And that is the question done. So use either way. This way is just a little bit quicker. We don't have to multiply as many things out, and it's kind of a bit more intuitive. You can just see that 5 is equal to that. You're just comparing terms pretty much. What I want you to remember is any quadratic form can be written like this, where you have one root plus the other, and then one root times the other. But make sure you have this minus here. Okay, great. So that is that question done. And on to the next one. Okay, so then we moved on to just a little bit of logs, and I ran through briefly what a log was, so let me just go ahead and do that again. Basically, what I want you to remember is log is the opposite of raising something to a power, and that's all I want you to take away. Just think of that. Log is the opposite of raising something to power, and the opposite of raising something to power is a log. So they go both ways. One is the opposite of the other, and why this is useful is because if this is the graph of e to the x, and then this would be the graph of log to the base e of x, otherwise known as ln of x. So what I did there was just kind of reflected about this axis, so it's kind of just the mirror image of it, and these can be anything. So this could be 2 to the power of x, and this would be log to the base 2 of x, and this could be 3 to the x, and this could be log to the base 3 of x, and so on and so on. And why this is useful is because they're opposites of each other. So if we have 3 to the x here, what we can actually do is take log to the base 3 of all this, and this will kind of cancel with this, and we'll just be left with the x. So then you get this. You just get the x, and you'll equal to something. So let's say we have 3 to the power of x is equal to 27. Okay, how are we going to get the x down from this power? Well, we know that the opposite of raising something to power is a log. So let's do that. Log to the base 3 of 3 to the power of ax, and to keep both sides equal, we're going to have to take log to the base 3 of this side as well. So this big 3 will cancel with that, and we're just left with x is equal to, and log to the base 3 of 27 is just a number in your calculator, and it should be equal to 3. So let me go ahead and check. So I'll type log to the base 3 of 27, and that is going to be 3. Perfect. So we know that 3 to the power of 3 is equal to 27. We know that now because this 3 was this, or this x was the 3. Perfect. Now, let's say we have the opposite. Let's say we have log to the base 3 of x is equal to 27. What are we going to do here? Or let's do 3. So log to the base 3 of x is equal to 3. Well, x is stuck inside this log, and what's the opposite? How do we get it out? We're going to raise everything to the 3. So log to the base 3 of x is going to be equal to 3 to the power of 3. So I just kind of stuck a 3 here and put everything on top of it. So now this 3 will cancel with this because they're opposites, and we'll be left with the x. And then this is just a number, and you put that in your calculator, and you get 27. So they're both opposites of each other. That's what I want you to take away. And one will cancel out the other. That's all. And here we just did a bunch of them. I might not run through them all. Let me just run through kind of this one here. So 8x is equal to 16. How are we going to get rid of this? Well, what's the opposite of raising to the power of 8? We're going to take log to the base 8 of all that. Then we're going to keep it equal on both sides. So we're going to take log to the base 8 of this. This will cancel with this. X is equal to whatever log to the base 8 of 16 is. 4 over 3. And you can check that because if you do 8 to the power of 4 over 3 in your calculator, you should get the same answer. And you get 16. Yeah. Great. So that's one of them done. Let's try find one in the opposite direction. Oh, there's no ones in the opposite direction. Let's do this one. Because it's good to know. Okay, so this one says 5 to the power of x plus 2 is equal to 125. Okay, it doesn't matter there's a plus 2. Our x is still stuck up in our 5, so what's the opposite of raising something to the power of 5? Well, it's log to the base 5. And then keep both sides equal. Log 5. This cancels with this. X plus 2 is equal to whatever log to the base 5 of 25 is. Log to the base 5 of 25, or 125, sorry, is 3. So x plus 2 is equal to 3. X is equal to 1. And we can check that because if x is 1, then 5x plus 2 is going to be 1 plus 2, 5 to the power 3. And you put that in your calculator, you get 125. Perfect. And let's do another one that I'm just going to make up here. Let's say we have log to the base 27 of x plus 2 is equal to 3. I might get a really small answer, a really big answer, doesn't matter. I'm just kind of making this up just to make the point that they're opposites. What is the opposite of... So our x plus 2 is stuck in here, and we can't get it out. What is the opposite of log to the base 27? Well, it's raising everything to the 27. So this will cancel with this, and we're left with x plus 2, and whatever 27 to the power of 3 is, which is a big number. 19683. Okay, so now x is equal to 19681, and that's your final answer. So this is all I want you to take away. Log is the opposite of x, and that's what it was kind of invented for, that because, log is the opposite of raising something to the power. That's what I meant. And it was invented for that because we needed a way to get things down from these exact situations. Someone was like, we need an inverse function. We need something that will undo that. And they just created that. It's very useful. Oh yeah, one last thing. If we have e to the power of x is equal to 72, say, what's the opposite of e to the power of x? Well, it's log e to the power of x. And we do that to both sides. But because this is used so often and it's so useful, this actually has a special name, and it's called the natural log, or ln. So we take ln of both sides, and it has a special button on your calculator. Those will cancel. X is equal to ln 27, and that's 3.296. Blah, blah, blah. So, that's just one last takeaway. E is the opposite of ln. Okay, great. That's what I want you to take away. Great. Okay, on to the next question. Okay, so another thing about logs and indices is that they have some rules. Some of them are kind of intuitive, some of them maybe not so, but they're all in your log tables anyway, all the ones that you'll need. And that's actually why they're called that. They're called log tables, but anyway. So yeah, they're all here. I think it's page 24 or something, I'm not too sure. That doesn't matter. And these are actually very useful. So my kind of advice maybe, it shouldn't happen, but God forbid it does, that if you're in a question and you hit a wall and you kind of get stuck, you don't know what to do, just kind of open this page and see if anything looks like anything we can use. And a good example of this is just this question down here. So it says, find the value of x where x is just a natural number, given log 2x plus 2 and log 2x minus 2 is equal to 5. Okay. We know that the opposite of log is raising everything to the 2, but the problem is that we have this plus in the way. Because if we raise both sides to the 2, we don't know whether we can just cancel both of these logs because we raised it to the 2. We don't know that. We know 2 raising it to the 2 is the opposite of 1 log. We don't know if it's the opposite of a 2. So what we're going to do is we're going to go to our log tables and we're going to see if it looks like anything we know. And if I just bring it up here, it is going to, in fact, look like this one up here. So here on the right hand side is going to be log something of something plus log something of something else. And most important thing here is that a and a, so we have the same base, 2 and 2, so perfect. Okay, so we're going to use this rule, and what this rule says is log to the base a of x plus log to the base a of y is the same as log to the base a of x times y. And you can actually just check this on your calculator. And this is kind of how they figured out these rules, that they just kind of messed around with this log function, and they saw that, oh yeah, if we take log to the base 2 of 5 and then add it to log to the base 2 of 6, and then we take log to the base 2 of 5 times 6 was 30, then we're going to end up with the same number. Okay, so here our x is going to be x plus 2 and our y is going to be x minus 2. So, and our a is just going to be 2, so that's log 2 x plus 2 times x minus 2 is equal to 5. So here, this is just the same as taking the log once and then multiplying together. Okay, now we know what's the opposite. Our x's are stuck in here in a log. What's the opposite of a log? Raise everything to 2. This will cancel with that, and this is just a number. So then we have x plus 2 times x minus 2 is equal to 2 to the power of 5 is 32. So that's 32. Now we want to find x, so we can multiply this out. So x squared plus 2x minus 2x minus 4 is equal to 32. So x squared minus 4 equal to 32. X squared minus, or x squared is equal to 36. X is equal to plus or minus 36. That's important. So because minus 6 squared is also 36, as well as 6 squared is equal to 36. So it can be either. And which one are we going to... We'll have to get rid of one. And the reason we're going to have to get rid of one is because logs don't work with negative numbers. Remember this picture I showed you here? So if this was e to the power of x and this was log ex, like that, we can't... These are your x values. So if we put in 2 here, you go up and you get a number. You put in 1 or 1.5 here, you get a number. Where it crosses is actually 1, and so anything between 0 and 1, if we plug in, and you can check on this calculator, if you plug in 0.5, so if you do ln 0.5, you'll actually get a negative number. That's because we're below the axis here. But what we can't do is sub in any negative x's, so we can get a negative output. So because our outputs are along this axis and it's below the x-axis, but we can't actually sub in, we can't have an input of, say, minus 2. And that'll reflect on your calculator. If you do ln minus 2, it'll just say math error. And so that's why we can't have negative numbers in logs, and that's why, let's check, we have log x plus 2 and log x minus 2. So if x was minus 6, it'd be minus 6 plus 2, so that'd still be minus 4. So we have a log 2 minus 4, so that wouldn't work. So we're going to disregard x equals minus 6, and we're going to keep the plus 6. Okay, so that is that question done. So on to the next one. So it says 2 log to the base 9 of x is equal to a half plus log to the base 9 of 5x plus 18. And here they give you a little hint. They said x is greater than 0. And that's because x can't be a minus number. Okay, so we're trying to solve for x. And so the first step in any algebraic solving is getting your x's all on one side and your constants all on the other. So let's do that. Let's do 2 log 9x, and then we're going to minus this. So minus log 9 5x plus 18, and then we're going to leave the half on that side, so half. Okay, so we're at this stage. We can kind of guess that we can use a similar rule to the one we used up here, because this is a plus and this is just a minus, so they're not too far off. What we have to check though is if we go up to our, yep, sure enough, there's our minus, but this one says log a x minus log a y, but ours is 2 log a 9x, and this rule up here doesn't have any kind of constant in front of this, so it doesn't have like a b or a c or anything like that. If it would, then we could use it, but it doesn't. So we're going to have to try to solve this little issue first, and then we can use that rule. So what is that issue? Well, that issue is that something is in front of the log, and this rule here kind of solves that. So this q here in front of the log is actually the same as taking the log of this and raising it to whatever is multiplied by. So if we had log to the base 2 of 3, and we multiplied that the whole thing by 3, that's exactly the same as taking log to the base 2 of 3, but cubing it. And if this one was 4, this would be to the power of 4. And it works the other way because it's exactly equal. So it works the other way. If we had something that looked like this, we could actually bring this power down and write it as 4 log 2, 3. Okay, so here we have 2 log 9x. So that's actually going to be exactly equal to log 9x squared minus log 9 of 5x plus 18 equal to 1/2. And now we can use our rule because we have nothing multiplied in front of the logs. So this rule says that any logs of the same base minus off each other is exactly the same as taking the log of one divided by the other. So these two are minus off each other, there's nothing in front of them. So we're going to head and apply this rule. So that's the exact same as taking the same log, so log to the base 9, but this time we're going to divide the first one by the second one. And then this is still going to be equal to 1/2. Okay, so we're trying to solve for x. Our x's are inside the bracket. We're going to try get them outside the bracket. How do we do that? What's the opposite of log to the base 9? Raising everything to the 9th. Okay, so these are just going to cancel, and this is just a number. So we're going to end up with x squared all over 5x plus 18 is equal to 9 to the power of 1/2 is just a third, or 3 if you put that in your calculator. And great, now we have something that looks a little bit easier than everything to do with logs. Here we just see it's simple algebra, so we can actually just cross multiply like this and get x squared is equal to 3 times 5x plus 18. Multiply that out and solve for x. So 15x plus 18 by 3 is 54. And then we're going to get a quadratic equation in x minus 15x plus 54 equal to 0. And we're going to factorize and solve, which you're perfectly capable of doing, and I'll leave you to do it. Okay, so that is a few more steps, but yeah, that's the idea. So these rules, really important. You don't have to learn them off by heart. They're in your exam or your log tables, but like things like these 3 basically will show up again and again in logs, and you'll basically just get to know them. Like you won't learn them off per se, but you'll just kind of pick them up, and they're kind of really useful. But yeah, so that's those 2 questions done, and those are kind of more abstract applications of where to use logs. Like it's kind of just arbitrary that we're trying to find some kind of x. In the next question, it's a little bit more applied to real life, and we'll just see what those look like now. Okay, so this is a typical exam question that you can get in relation to logs, and they usually follow the same format, and they're applied to things like diseases or injections, or basically things that kind of evolve like that, where they kind of double in each time like this, or they decay really fast like this. So if you think about infectious diseases, if this is your axis here, this is patient 0, then he infects one person, and then that person infects 2 people, and then each one of those people infects 2 people, so that's 4, and then 8, 16, that kind of thing. And here in this question, it's to do with injections in your body. So you inject a certain amount of drugs in your body, but it decays, and this time by 0.6 each time. So if this was 1, then 0.6, then 0.6 times 0.6, and then so on and so on. So that's why logs are kind of used here. You don't really need to know that for this question, but yeah, let's just jump in. Okay, so it says Alex gets injections of a medicinal drug. Each injection has 15 milligrams of the drug, and each day the amount of drug left in Alex's body from an injection decreases by 40%. So the amount of drug in milligrams left in Alex's body T days after a single injection is given by this. So basically what this means is T days after a single injection. So we inject Alex with uh, an injection of the drug, so 15 milligrams of the drug. So we inject him with 15 milligrams, and then 7 days later, say, we multiply all this out and we'll get some kind of a number, and that's this number here is how much drug is left in Alex's body. And so what this might remind you of is kind of the functions we were dealing with earlier. So there we had a function x squared plus 5x plus 7 or something, and we subbed in x's. So we subbed in f of 3, we said was 3 squared plus 5 times 3 plus 7, and we got some number, whatever that is. So our output was equal to some number, say 7. Okay, here we have the exact same thing, but this time they've just left out the kind of notation. So they could write, what is it? It's a drug. So let's write dt is equal to this. So we could write the function d with an input of t is equal to 15 times 0.6 with t. Okay, so that means that if we wanted 3 days after, so we sub in 3 days for t, so that's 15 times 0.6 times 3, and this will be just some number, pretend it's 21, and exact same thing. 21 is our output. So we subbed in 3, and we got an output of 21. Okay, great. So we want to find the amount of drugs left in Alex's body 2.5 days after a single 15 milligram injection. Give your answers in MG correct to do decimal places. Well, that's easy. Then once we know what we're looking at, easy. So we want 2.5 days. So the function at 2.5 is 15 times 0.6 times 2.5. And that is it. We put that in our calculator, and whatever that turns out to be, 6 times 2.5 is 4.18282.014, and that's where my calculator ends. They want to 2 decimal places, so we're going to round up from here, so 4.18, and we round down because it's 2. It's less than 5. And this is how many milligrams of the drug are left in Alex's body, so this is our output at 2.5 days. And what this would look like is, if this is our function here, and they decay like that, we sub in 2.5, and we go up to the function and see how much is left, and 4.18 milligrams is left. So up here is at 0 is 15, and then it gets lower, lower, lower. Okay, so that's what that looks like. So here it was 4.18 milligrams. Okay, now it says, how long after a single milligram injection will there be exactly 1 milligram of drug left in Alex's body? This is same question, but now it's reversed. So now our output, so d of some t, is going to be 1. Our output is 1. We have 1 milligram left. So if we go back to our graph over here, this is t. So, sorry, let me ignore that for a second. So we start at 15. We wait until we get to 1 milligram. Then we're going to go across and see how long that took. So t days. So that's the exact same. This is our t-axis, and this is our output. So this is dt. So d of t is going to be 1. That's exactly what we did. We subbed in t, and we got 1 left. And now we're going to try to see what 1 is. Okay, what's dt equal to? Well, dt is just the exact same as writing 15 times 0.6 to the power of t is equal to 1. Okay, and now we want to find t. How are we going to do that? Well, first step in finding any algebraic expression or getting any variable on finding any variable, solving for any x or any t, we want to get all the t's on one side and all the numbers on the other. So here we have two things multiplied together, and we're going to get rid of that by just dividing both sides by 15. So that means 0.6 of our t is equal to 1 over 15. Okay, great. Now you can see why we went through all this stuff before about how to get it down. We have the t, but it's stuck up in the 0.6. So how are we going to get it down? We're going to take log 0.6 of both sides. Just make a bit of room. And log 0.6. And this here is just a number. Okay, so this log 0.6 will cancel with this. And we're just left with t is equal to log 0.6 of 1 over 15. And what is that? Let me check on the calculator. Log 0.6 of 1 over 15, 5.30. 5.30. So after 5.3 days, there will be exactly 1 milligram of drug left in Alex's body. That's what that means. So over here, back to our picture, if we inject him with 15 milligrams and we wait till there's only 1 milligram left, that will take 5.3 days. Perfect. Okay, so that is that question done. Okay, so next question, again, very similar, and you begin to notice trends like this where certain questions, they tend to ask in certain ways, and this is, again, the same kind of thing. So it says, number of subscribers n to a new mobile phone network can be modeled using the function. Okay, so this time, at least they've told us it's a function, but now we understand that this is our output and this is our rule. So we're going to be subbing in something for t, and we're going to be getting some number of subscribers, n. Okay, great. And it says where A is the initial launch of users. So this A here is the amount of users when they first started, when T is 0. And T is the number of months. So this is important. Don't think it's days like last time. Number of months after the network launched. At the initial launch on January 1st, 8,500 users subscribed to the network. 4 months later, 22,500 people have subscribed. Using the above information, find the value of A and the value of B. Give B correct to 4 decimal places. Okay. So we have our function nt is equal to ae to the bt. Okay, we know if we draw this out, it's going to look something like this, and it'll get exponentially bigger. And so this here is our value for a. This is the output when we just start, when t is equal to 0, so we don't go out. This is 1, 2, 3. We don't go out any spaces. We just start right t is 0. And so n is actually going to, or a is actually going to be equal to n of 0. So when t is 0, that's our initial number of users. We don't have to wait any time to get them. They're initial, they're already there. So n0 is how many? 8,500. 8,500, and that is when t is equal to 0. So the number of subscribers at the very start when t is 0, no time has passed, is 8,500, and then we sub in 0 for t and see where that takes us. So 8,500 is going to be equal to ae to the power 0, and anything to the power 0 is just 1. That's one rule that you might come across a lot, and it's useful to know anything to the power 0 is 1. So then 8,500 is just equal to 8 times 1 is 1, or 8 times 1 is a. So a is equal to 8,500. Perfect. So now we can update our kind of function up here. So instead of a, we can have 8,500 times EBT. And now we want to find B. So we've kind of hit a wall here. Don't know where else to go. We're going to need some other bit of information. And the bit of information we haven't used in the question is 4 months later, 22,500 people had subscribed. So that means, again, if we draw it out, if this was our function and this was 8,500, this means 4 months, so this was 0, 1, 2, 3, 4. We go up till we hit the function, and this is, what was it, 22 or 25, 500 or something, 22, 500. Okay, and this is our output. So what's this? This is our output when t is 4. So this is n4 is 2250. Okay, so n4 is 2250, so that means 8500 e to the power of b times 4, because t was 4 here. Okay, and now let's see where that gets us. So we want to find b. Same thing as before, we want to get it on its own, but this time it's multiplied by 8500. So we're going to divide across, so 20,500 over 8,500. Those zeros are going to go, and we're going to get 225 over 85 is equal to e to the power of 4b. Okay, so our b is stuck up in our e. How are we going to get it down? Well, do you remember I was saying the opposite of raising something to a power is log, but the opposite of raising e to the power is log to the base e, which it worked the same in the calculator, but another way to write this is just ln. So you can do log to the base e in your calculator, or you can do ln, it really doesn't matter. So that will cancel with that. This here is just a number. Why don't we leave it as it is for now, because it's kind of a long decimal. And this is, we're left with 4b on this side. So we want b, so we can just divide the whole thing by 4. And we can put all this in our calculator and get some number for b. And let's see what it is. ln 225 over 85 all over 4. b is equal to 0.24336 and something something. But they want it to 4 decimal places. So 0.2434. And that is the answer for B. So yeah, on to the next part of the question. Okay, so next part of the question says, if the network continues to grow at this rate, how many users will have subscribed 1 year after launch? Okay, well, it says the network continues to grow at this rate, so that means we're still going to use the same function. And now we have values for A and B. So we have 8,500. E to the power of, and B here was 0.2433, and that's multiplied by T. Okay, and so we want to know how many users will be subscribed. So what is the output 1 year after launch when T is not 1, because T is number of months, when T is 12. So N, what is the output when T is 12? N of 12. And that's going to be 8,500 e to the power of 0.2433 times 12. And plug that into your calculator and you'll get some answer. And that is the whole question done. Easy as that. Okay, and very last one, it says, after how many months will 45,550 people have signed up the network? So same kind of thing. Our output now, N of T, is going to be 45,550. And that is when, or we want to find out how long that takes. So e to the power of 0.2433, and we want to find t. So same thing, working in reverse. We want to get t in its own, so we're going to divide by both sides by 8,500. 8,500. Then we're going to be left with 0.2433t. Then we're going to take ln of both sides. Ln of this. So those are going to cancel. And then we're going to get ln of this over 0.2433, and that's t. And whatever many months that is, I don't know, let's just pretend, call it 18 months. That is your final answer. Okay. So that is that question done. You can see they kind of reuse kind of the same format. They usually say find how many will have subscribed after a certain amount of time, and then they say how long will it take to get however many subscribe, that kind of thing. They do the opposite each time. Just depends if they add this little bit of extra at the start where you have to actually make the function. So you have to find 8,500 and 0.2433. But yeah, that's the question done. If one of those questions came up in your Leaving Cert, I'd be very happy. Fairly formulaic, and yeah, no trouble for you. So yeah, on to the next question. Okay, so very last question, fairly straightforward one, but it says our function here, t, capital T of t, gives the temperature of the coffee at time t. If the ideal temperature to drink coffee is 82 degrees, find the time to the nearest second that it takes for the coffee to reach this temperature. Okay, so we want our output to be 82 degrees. So capital T of t is going to be 82, and all of that is going to be 75 e to the minus 0.081 t plus 20. So we want to find t. So how are we going to do that? Same thing as before, just slightly more complicated. We're going to get t on its own, then get the log, and then divide. Okay, so how are we going to get t on its own? Well, first off, we're going to minus this 20, so it's going to be 62 is equal to 75 e to the minus 0.081 times t. Now we want to divide by this 75, so why don't we just do it this way? Then we're going to get rid of the e, so we're going to take ln of both sides. This, cancel with that. So that'll cancel with that, and we're just left with minus 0.081. And now we're just going to divide the whole thing by minus 0.081. And that is going to be equal to t. And so plug that into your calculator and see, find the time to the nearest second. So yeah, find t to the nearest second. You're going to get it in decimals, so you'll get like 5.6 or something. And so you're going to have to convert that 0.6 into seconds, but you can definitely do that. Okay, so that is that question done. That was our very last question. So yeah, last week we did a bunch of this log stuff. It's a great question if it comes up. Really easy to wrap your head around, and I think you should be more than capable to answer them. But yeah, just remember, this is your output. These are your rules for your input. And if we want to work backwards, we want to get t on its own and then use the fact that log is the opposite of indices. And then they cancel off each other. They reduce down the power, that kind of thing. And then we can use our rules if we really need to, like we saw in the algebra questions. But yeah, really lovely questions. And I'd be happy if they came up in the Leaving Cert. Okay, so that's all of them, and I will end it there, and I'll see you next week.